Okay, hopefully you have the audio from my headphones now. So what I'm going to do is basically just share my screen, and I'm going to show you a lot of really text-based stuff about what's happening in TiDB when these queries are executed. So let me share the right window. Hopefully what you see here are these queries that we just talked about. So these are just in an editor on my Mac, and I'm connected both to the Aurora instance. This is the live Aurora instance that we were just using, and this is the live TiDB cluster that we were just using for that demo that Chunha did. So I can take these queries and we can actually look at the explain output for them. So if I paste this here, execute that. Whoops, I did that wrong. Let me try to redo that. So this is the problem. It takes a while when we do it on Aurora. So now I'm going to redo the explain here. So here we can see the query execution plan for this query on Aurora. And what we notice is kind of this is the dreaded execution plan for a MySQL database. We have null possible keys. It can't use an index. It's just going to have to scan the table. It's also going to use a temporary table, and it has to do a file sort. So we're kind of hitting all the marks here for why this query doesn't perform well, when we saw that it takes about 10 seconds in Aurora. So let's try the same query now in TiDB, and we'll see the explain plan here looks a lot different than it does for MySQL. So if folks in the call are not familiar with TiDB and what TiDB explain plans look like, I'll just take a moment to provide a little bit of detail about that. So instead of the normal explain plan that we see here, where it's kind of all just what's happening on a table by table basis, we actually split out all of the information that's happening in the explain plan into a step-by-step query execution diagram, basically. So you see that this is indented. It's showing us down here that there's a table scan actually happening, but we can see based on this part that the table scan is happening in TiFlash. So what is TiFlash? Well, TiFlash is the column store component of the TiDB cluster. So we're not actually getting the data from the row store. While Aurora has to scan through basically what is a glorified InnoDB table space to get the data, we're able to use a column store. Well, why is that better? Column stores are really useful for analytics. So in this case, this is kind of an analytical query because we're doing a group by and we're doing an aggregate. In this case, the aggregate's a very simple count star. But when we execute this, we can see that it executes in TiDB, as we saw earlier, in like a fraction of a second. Whereas in Aurora, when I accidentally executed this query, it took about 10 seconds. The reason is that in the execution plan, we can see that we're pushing down all of the work for this query into TiFlash. TiFlash is actually able to collect together all of the details about this almost instantaneously and return them back to TiDB. Some people might ask, well, hey, if you know you're going to do this kind of query on Aurora, you can add an index. Well, it's not that easy to add an index. If we look at the table, we'll see that we have this event time column, and that's what we're actually using for our grouping and our ordering. And if you know you want to group by date, then you have to add a new column that has the date, or you have to add an expression index on just the date. And then you might be able to use that secondary key to provide an efficient execution plan. But the cool thing about TiDB is it's not just the date. We can do by week. And it's going to be just as fast. We can do by year or by hour, and it's going to be just as fast as it was when we grouped by date. So if you wanted to get that flexibility in a system like Aurora, you would have to add secondary keys for every one of these different dimensions over the event time column. So that's one thing we bring to the table with TiFlash, is that you have this really flexible way to execute these analytics queries. And this data, even though it's coming from TiFlash, is completely in sync with the data that's in the row store. So in TiDB, the row store is the authoritative data store, and TiFlash, the column store, is always in sync when you execute a query. So we're getting analytical query performance from a column store that's synchronized with the operational transactional row store. Let's take a look at the next query and see how that one compares. It's really going to be a similar story. So again, same thing. we got no keys, we can't do anything. It's like, again, this like classically ugly query execution plan for a MySQL compatible database. Then on TiDB, once again, we're pushing all this work down into TiFlash. TiFlash is scanning the table, but using the column store and returning results in a super efficient way. Things get a little bit more complicated, of course, here when we start doing a join. So the previous two queries were only using a single table. They were only using the events table. Now we're joining the events table with the collections table and the assets table. So how does that affect the execution plan? Well, let's take a look at what we get in Aurora for this one. Now, Aurora has a couple possible keys here, but it's choosing no key. And part of the reason for that is that it decides that it's going to have to scan that table anyway when it joins it against the other tables. So when we do this query in Aurora, I forget how long this one took. It took, I think, quite a long time. I guess we can start that up while I show you the behavior of the same explain in TiDB. So we'll just execute that and come back to that later. Meanwhile, over here, we see this execution plan where, again, it's not only pushing down the computation to TiFlash, but it's actually pushing down the entire join to TiFlash. So we can see here, when we see stuff like exchange sender, hash join, all of these things, all these senders and receivers are actually part of the MPP framework inside of TiFlash. MPP is massively parallel processing. So you can basically continue to add TiFlash nodes to your cluster. Data will automatically be spread across those TiFlash nodes. And then anytime you execute one of these analytical queries, all of the TiFlash nodes that have relevant data will talk to one another to resolve the query, and then they will collectively return the results of the query to the TiDB server. So that's how you gain this scalable analytical performance in a system like TiDB, where again, we have the authoritative row store, and then we have the scalable push down column store where we can use MPP to execute queries on the storage nodes themselves and return the results to TiDB. So if we execute this query in TiDB, I forget, this one's like 1 second maybe or something like that. Okay, about 3 seconds. And over here it was 23 seconds in Aurora. So that's a pretty big difference, right? And again, in a lot of these cases, it might be possible to make these queries in Aurora a little bit more efficient by adding some indexes, by changing the structure, by either denormalizing tables or restructuring things so that you don't have to do joins. But that kind of goes against the idea of making a relational database work well and having a data model that makes sense and making transactions usable. So being able to leverage something like TiFlash allows you to execute these analytical queries while maintaining a reasonably normalized database, using RDBMS concepts that you're familiar with, and not having to get a bunch of hacks in place to kind of force RDBMS to use analytics by doing a ton of denormalization or something like that, or having to maintain 1 million secondary keys. Finally, this last query, again, this is probably going to be a really similar story. I'm saying probably because I'm doing this live. We're watching what's happening. This is the live system. This is live data. This is, kind of a classic explain plan. So I don't know that there's a whole lot we could do to improve that. But if we execute this select here, we'll go over and see how this one looks in TiDB. And, again, that's a very similar story where all the work for this analytical query is being pushed down into TiFlash. You're seeing here that the actual summation operations are being pushed down as well. Let's see if I can figure out where that's actually happening here. Yeah, so we're seeing that the sum function is actually pushed down into TiFlash. So again, in a scenario where you had multiple TiFlash nodes, each one of them will be doing its own work to sum up the data that it had, coordinate that with the other TiFlash nodes, and then they would all be able to send that back up to the TiDB server where the query is being executed. So this one's going to take us 0.7 seconds, and over here took us 44 seconds. So a difference of like 50 times faster. That sort of speaks for itself. And I believe that this cluster, Chen Hao, correct me if I'm wrong, but I believe this cluster only has a single TiFlash node. Is that right?
Single type. Yes, that's right.
Yeah. So MPP in this case, there's nothing really parallel that's happening, but you're pushing down the functionality, the execution, the computation into the storage node. And you would expect as you grew to have more storage, it would make sense to have more TiFlash nodes. And then again, the data would be spread across those, and those nodes would be working together to resolve the query. So we not only have the scalable key value store in TiKV, but we also have this scalable column store with scalable cross-storage, multi-parallel processing that can happen. So one other thing I want to point out while we have a moment, if we go back and look at some of the earlier queries, well, scrolling back in my CLI is a little bit painful, so I'll just copy this one again. But one thing that's pretty cool, so I showed you how we can see that this is using TiFlash. In TiDB, we can tell it that we actually want to use TiKV for this and see what that looks like. So we can read from storage TiKV, and we'll give it the events table. So that shows us, and now instead of using TiFlash, we're actually going to be able to push this down to TiKV. I think for this query, it's not going to make a huge difference in performance because, again, we have a single TiFlash node. It's a relatively straightforward table. But let's try to just try to compare and see what happens, just for fun, what happens in terms of performance here. So this query takes 1 second in TiKV. So this is not using TiFlash even in this case. And I don't remember how long that one took here, but let's see what that one took in Aurora. I think this took like 10 seconds in Aurora. I was going to have a drink of water, but my water is empty, so I'll take the time to pour myself more water. So again, the first query, we showed over here that even using TiKV, not even using TiFlash, we still have a 1 second query execution time. The same exact table structure over in Aurora, same query, took 10 times as long. And that, this is not really necessarily an analytical query. This is just a query doing a simple count star. And that was still way faster in TiKV than it was in Aurora. And for the more intense analytical queries, we can see that the payoff of TiFlash in the TiDB cluster is that much more. So that's basically what I wanted to demonstrate. I wanted to show you guys how to use explain to compare the execution plans between Aurora and a TiDB cluster. I wanted to talk about how TiFlash works, how TiFlash is part of the TiDB cluster. It's in sync with the TiKV row store, and you can see the comparison in performance between these two solutions. So that's what I wanted to share. I'm happy to answer questions.